Hello everyone, I'm Aditya Tandon and I work at the Institute of Digital and Autonomous Construction at Hamburg University of Technology. And today I will present our research work or titled BIM-based human-robot collaboration for building inspections using mixed reality. Part of this work was conducted as a part of the DFG project based on structural health monitoring and inspections. Traditionally, building inspections have been mostly manual, it is possible to perform building inspections completely autonomously with mobile robots. However, it can be seen that there might be situations where inspection tasks can either be repetitive or extremely computationally demanding, and mobile robots can assist human inspectors with performing these inspections. These inspections can therefore be performed in human-robot teams. However, there are a few challenges before these inspections can be performed collaboratively. Number one is that there is a lack of shared digital environmental information between what's perceived by the humans wearing the mixed reality headsets and the robots. The second challenge has to do with lack of intuitive interfaces for allowing control of the robots by human operators. Our objectives are to utilize geometric and semantic information that is present inside BIM models to actually augment the virtual environment models. And at the same time, we want to develop mixed reality-based human-machine interfaces that allows effective interaction between the robots and human inspectors, and also use this information that we extract from BIM models to create digital environment overlays on the actual inspection environment. So we propose a framework that uses both building information modeling and mixed reality. And before we go into how the framework actually works, it's important to understand the different frames that are involved. We essentially have the BIM model frame B, which corresponds to the reality. And at the same time, we have a map frame M, which is where robots usually operate. And the third one, and the most important one, is actually the headset origin frame, which is also coincident with our virtual environment. So we have three major frames. And what's really nice is that the frames are directly related to one another through a simple linear transformation, which can eventually be identified, allowing robots to work alongside humans with information from the BIM model. The actual frames between the robots and the map, and the robot and the mixed reality headset and the virtual world or the MR headset origin frame are actually given by the localization systems of both the robots and the mixed reality headsets. So to go a little bit deeper into how this framework works together, we start off with BIM models and utilize all sorts of information about the geometry and semantic information that's there to enrich our virtual environments. So a virtual environment can then be created based on the BIM model, but what's interesting is that we must align both of these and find the fixed linear transformation between the two. That can be expressed with this transformation, BTHO, which is then a linear transform between the BIM model and the virtual environment. And the MR headset, the position of the MR headset in the virtual environment is already known through the internal localization system. When we want to utilize this with robots, what we actually have are robot navigation maps, and those are also known directly. So the position of the robots is known directly in the robot navigation maps through their own localization system. But somehow these navigation maps need to be tied in with the BIM models and the virtual environments. And one option is to directly relate the robot navigation maps to the BIM models using fiducials. But what is even more, what could also be used as an alternative approach is to directly align the robot navigation maps with the virtual environment. And the advantage of doing that is that when we figure out this transformation HO to the map, we can directly calculate the position of the robots within the virtual environment, allowing us to not only give information back to the virtual environment from the robot, but also to command the robot directly in the virtual environment frame. This leads to three interesting transformations: the one aligning the BIM model with the virtual environment, the one with the robot navigation maps to the virtual environment, and ultimately the robots in the virtual environment directly. To do the first part and figure out the transformation between the BIM model and the virtual environment. What we do is we can utilize a fixed marker. This is also known as space pins, which can then be added to the physical environment, which is also coincident with the BIM model, and can also be added to the virtual environment. So if we are able to scan these space pins using the MR headsets, what we can do is we can directly complete this transformation chain, allowing us to determine the linear transformation between the BIM model or the real world and the virtual environment. In this way, we can determine this critical transformation. The second step involves aligning the virtual environment with the robot navigation maps, which means determining this transformation as well. A similar approach can be utilized since we already know where the robots are in the navigation map through the localization system. And we already have the position of the MR headsets in the virtual environment through the internal localization system of the mixed reality headset. What we can do is actually add these space pins on our robot, and then also scan these space pins directly from the mixed reality headset, allowing us to, when we close the transformation chain, we can then determine this green transformation and also this red transformation. Additionally, what we do in our framework is we develop intuitive digital interfaces for allowing humans and robots to interact with one another. Specifically in this case, you can see that a human operator can ask the robot to navigate to a custom navigation waypoint after the worlds have all been aligned together. So as you see here, the robot navigates to this specific navigation waypoint. We then validate our framework by testing the accuracy and efficiency. As step one, we align the virtual environment with the physical environment using these QR space pins. And when these space pins are then aligned, you can see that we get a good transformation. A red marker is created at the base, which signifies that the alignment is complete. And the second step to align the virtual environment with the robot navigation maps, we calculate the transformation and then can get the robot to move to the actual position, which is then signified by this red marker that's been laid in the real world. Once these two steps are complete, we know that the virtual environment has been aligned with the physical environment, and we also know that the navigation maps for the robots have also been aligned to the virtual environment, allowing us to validate the overall framework by performing an inspection mission. So as you see, we can directly select a BIM element and say this BIM element needs to be inspected, and a command can then be given to the robot to navigate to that BIM element. Out here, the green position is actually the inspection pose marker, and all of the elements that you see directly with the yellow points are actually game objects that have been created in the Unity world to allow this sort of task execution to take place. Lastly, we also try to look at the efficiency of the framework by doing concurrent inspections, which means you don't utilize only one human and one robot, but we can actually utilize multiple robots to perform these inspections alongside the humans. So as a last step, we can see that there are certain tasks that are better performed by humans, which may be out of reach for the robot. And in this method, we can allocate tasks based on capabilities of humans and robots both to perform these inspections in a more effective and concurrent manner. While all of this sounds really nice, there are definitely a lot of challenges. Number one being scalability, lighting, and connectivity play major roles that inhibit this from real-world deployment. And practical barriers also include the high implementation costs, the training needs, and obviously safety compliance to ensure that human-robot collaboration is safe. And in future work, we look at exactly this and how we can integrate more safety mechanisms to ensure secure human-robot collaboration. And at the same time, how we can improve the localization accuracy of the robots and the human workers wearing the headset by introducing a fixed constraint between the headset and the robots directly. Yeah, and I think that's all from my side. Thank you so much for your attention, and yeah.